everything can be covered. So there'll be some favorite things that you may be startled have been left out, but I think there'll be some interesting things that you'll see that you haven't seen before. So without further ado, let's get started here. Think back to around 1900, so about 121 years ago. This is a period in which the United States was going through a very rapid industrialization. Factories were popping up. People were moving from the farms into the cities. The standard of living was rising because of the many manufactured products being lower in cost than the handmade products of previous eras. But there was a serious problem, and the problem was that the buildings in which manufacturing took place were the same types of buildings, generally speaking, as had been constructed for hundreds, if not thousands of years. The latest development in these buildings was what was called mill construction or slow burning. And they were called mill construction because they were the buildings that were constructed for the mills that were out on the East Coast and the New England area. These buildings, structurally speaking, they were made of brick. Exterior brick walls are what held the building up, and the interior of the building was supported by a framework of timber and sometimes a little bit of iron to hold the timber together, and the floors were all made of wood. So you can imagine that fire was obviously a serious problem. And if the building didn't burn down, then the serious problem was the high cost of insuring against fire. Second problem was the inadequate illumination. So the outer walls of the building supported it, which meant that the larger the windows were, the weaker the walls were, so the walls had to be made thicker. So it was always a compromise between the amount of window space and the strength of the wall. And finally, vibration, because manufacturing as it grew tended to use heavier and larger equipment, and that equipment would shake the floor. And that resulted in the inability to make very fine types of cuts when cutting machines were used, and machine tools tended to wear out sooner because of the vibration. So here you see a typical example of one of those buildings. It's a mill construction building. This is the Michigan Stove Works factory on Jefferson Avenue, about halfway out to Belle Isle, for those people familiar with the Detroit area. The building was built in 1890, typical brick and timber type of building. And the Michigan Stove Works, as a matter of fact, was the largest manufacturer of stoves in the world until it burned down. And you can see here, I've outlined in red exactly where that massive building was. And there's only a little bit of it left, a little bit of the corner of the building sticking up. So not only was the building gutted, it was totally demolished. And over on the right, you can see another part of the stove works. You can see how the walls were constructed, but all of the floors, columns, the beams, everything was burned out, along with all the contents of the building, obviously. And more to the point, for Detroit, the two largest automobile companies in the city both burned to the ground. The one in 1901, the Oldsmobile factory, and the other in 1904, the Cadillac factory. As a result of the increasing location of factories in the cities, the increasing number of fires, the larger size of the buildings, making it more difficult to fight the fires, insurance companies were being dramatically damaged. Many of them actually just simply went out of business, went bankrupt, or refused to write fire insurance policies. And at one point, I think around 1901 or 2, they raised the price effective immediately of all insurance policies on commercial and industrial buildings by 25%. So enter the Kahn family. You see here Joseph and Rosalie Kahn with their large brood of children. All of these children from 1881 on were born in the US, but prior to that, those children were all born in Germany, which is where the Kahn family immigrated from. Julius and Albert, you see in the middle there. Between them was Gustav, or Gus as he was called. Gus and Albert did not have the benefit of college education, but starting with Julius, all of the boys went to college, and at one point or another, they all worked for either Julius or Albert or both of them in their firms that they would develop later. Molly, as a matter of fact, was an excellent businesswoman. She built a company that her father started into a very successful business that operated until the 1970s. Albert was much of a genius when it came to anticipating future trends. I'm not sure if it was innate or if he did a good job of reading the newspaper, but he anticipated not only that Detroit would need more factories, but that the factories would have to be much larger and far more complex than the factories that existed at that time. He also anticipated, and this was a very important factor, that engineering would become much more important in designing factories than architecture. And if he wanted to maintain his business as an architect, he would have to consider that engineering was going to be an important part of designing industrial facilities. And the reason that he was interested in that in particular was that the industrial design work was much more lucrative. A typical home that Albert might design might be worth $10,000 or $20,000. So his take of that would be 5 or 6%. But an industrial factory would be closer to $80,000 to maybe $200,000. So much more lucrative and not that much more work. But here's Julius. Julius is a German-born immigrant. He was born in 1874 in Germany, came with his family to the US in 1881, was educated in Detroit schools, and to a great part owes his college education to Albert, who at the time was working and earning enough money that he could afford to help pay for Julius's education at U of M, where he became a civil engineer. In 1902, Julius had a fair amount of work experience, and most of this was in engineering that involved steel structures. And Albert decided that it would be a smart move for him to partner with Julius and thereby bring engineering into his firm. And in doing so, Kahn & Kahn, which the new firm was known as, became the first architecture and engineering firm in the city of Detroit, and one of the very first architecture firms to include engineering, one of the very first in the nation. And that is probably the greatest contribution to why Albert became such an important architect in the future. Albert and Julius were both very much aware of the reason for building industrial structures, which is the purpose of which was to make a profit, that the owners needed to view these structures as investments. And Albert at one time stated very specifically, the plant must be economically designed, it must serve as an investment. Industrial buildings deal largely with practical requirements, structural design, and mechanical equipment. So essentially saying that it's much more the role of the engineer to design a factory than it is the architect. The key things that Albert and Julius understood that owners needed to have was the ability to construct factories quickly, low initial cost for these industrial buildings, that the buildings have minimal maintenance and insurance cost requirements, and that the buildings be designed in such a way that it contributed to the increased efficiency of manufacturing and the reduced labor costs that would come by having greater manufacturing efficiency, not moving the parts and pieces of the manufacturing process moved around as much. The very first important job that Albert and Julius secured was the design of the new Packard Motor Company plant in Detroit. Packard had a plant in Ohio. The company was bought out by Detroiters. They intended to move the plant to Detroit, and they hired Albert and Julius to design this new plant. And one of the interesting things that was discovered when rummaging through the plans for this 1903 building was the way in which Albert and Julius promoted themselves as a team comprised of an architect and an engineer, to the extent even that they wrote that actually on the plans for the building, which is what you see right here. This is a piece from one of the architectural drawing sheets for the Packard plant. Now, for some of you who are well aware of some of the architectural history that we're talking about, this is the 1903 plant, not the plant that was constructed later of concrete, known as building number 10. This is the original blank sheet from scratch design that Albert and Julius came up with. The plant was a huge success. And the reason it was a success is because it was simple and easy to construct. The plant was up and running 90 days from start to finish, so that production could begin immediately. The buildings were engineered in such a way that the fire insurance costs were reduced significantly from what similar buildings in the area were paying for their insurance. Material handling, moving materials around the plant were minimized, reducing the cost of producing whatever the plant was producing, in this case, Packard automobiles. Individual motors were run for each department. Normally, what you'd have in a mill design building, you'd have one massive motor or a steam engine running all the equipment in the plant. But they engineered it in such a way that any department could be shut down without having to shut down the whole factory. And finally, and oddly enough, the design incorporated a method by which all workers could enter their department where they worked from the outside of the building without having to travel through other departments within the building, thereby reducing labor costs. And that was the result, obviously, of distraction. So here you see a comparison between the Ford Piquette plant that was actually built a year later, designed by Field, Hinchman, and Smith, just a big box within which the various parts of production were settled wherever they could be found a space large enough. The Kahn and Kahn design, Packard plant, was spread out, essentially anticipating what Henry Ford would do years later with the plant that he built at the River Rouge. So the production was distributed through different buildings, and each building had a specific task that took place within it, and that building was designed specifically for that task. Now, we're going to go back to the year before. This is when Julius was part of Kahn's firm, but they were building the Palms apartment building, which was designed by George Mason and Albert Kahn. It was a fireproof building because that was becoming very important at the time for obvious reasons. And to make it fireproof, Albert did something that nobody else in the city of Detroit had yet done, and that was to use concrete, reinforced concrete, to construct the floors of the building. Now, this is, as I said, the first time it had been done in Detroit. No other companies in the city had experience installing these floors. So the company that was hired to do this installation was the Cleveland Silex Stone Company. Their specialty, installing concrete sidewalks. Well, this puzzled Julius. He couldn't understand how the concrete floors could be planned if there was no way to determine how much weight they could support. So he asked Albert, how do you calculate the strength of reinforced concrete? And Albert responded by guess. There are no scientific data. I suspect that Julius could come back to that. It's lost to history, though. But here's what the problem was. reinforced concrete, when it's overloaded, fails unpredictably. There's no way to know exactly where the concrete is going to shatter. And because of that, there was no way to calculate how much weight a beam could support. So at the time, concrete buildings were very expensive because a great deal of excess concrete and steel had to be put into the building in order to assure safety. Now here is, now I realize this is getting a little bit into the weeds of the engineering, but this is actually very simple and quite interesting. When you load up a beam, what happens is the bottom of the beam is placed in tension. That is, it's forced to stretch or get longer, whereas the top of the beam is in compression. It's compressed because it's getting shorter. And so you have these two stresses that need to be dealt with in terms of designing a beam. Now, Julius was very familiar with steel trusses, which are used for bridges and many different constructions within steel frame buildings. And he understood exactly how they worked and why they worked, and the fact that the steel could be used to build something, and you could calculate exactly how much load that object could safely accommodate, and thereby be able to build something economically, making it just strong enough to do the job it had to do and have a measure of safety built into it. And just like with the beam that I just showed you, the bottom section of the truss resists tension. The top section of the truss resists compression, and the wings or pieces that run in between, some resist tension, some resist compression. Julius had the idea of enclosing one of these trusses within a steel beam. Then he would know exactly how much weight the beam could support, because he'd know exactly how much the steel truss could support. He also realized something very important, that because the truss is embedded in concrete, you would not need to have any of the sections that resisted compression, because the steel being surrounded by concrete, the concrete itself would resist compression. So you could eliminate about half of the steel truss. Now, the advantage of that is that compared with a regular beam that had a single bar running across the bottom, the Kahn bar wouldn't be able to slip within the beam. The wings would hold it in place. The wings also would cross the cracks that would develop vertically in the beam at right angles and prevent those cracks from expanding and ultimately causing the beam to fail. So with this in mind, Julius went about testing his beams, and he found that every single beam that he tested using his special trussed steel reinforcement bar, the beam would always fail in the center when weight was overloading the beam, which meant that the way that the beam failed was by the reinforcement bar snapping in half near the center of the beam. And because the steel was failing and not the concrete, Julius was able to calculate exactly how much weight the beam could support. And this was essentially Julius's revolution in developing a practical and scientific method of reinforcing concrete. Now, there was one other problem that Julius felt he had to overcome. If you look at these ceilings, they're supported by beams and joists and girders, and you can see that there's a lot of them. And as a consequence of that, when you were building the formwork to construct the building, you had to create a great deal of wooden forms. And these wooden forms were very labor intensive to construct. They used an enormous amount of lumber, which had to be acquired locally, and added a lot of expense and effort to the project. Julius came up with a way to eliminate a lot of the formwork that was involved in constructing these buildings. He would start by just building a simple wood flat platform for the floor that was going to be constructed. And on top of that, he would lay in terracotta blocks. The blocks were very light because for the most part, they were just air being hollow. So they were much lighter than if you were building the floor out of solid concrete. Then he'd lay his reinforcement bars in the spaces between each of these terracotta blocks. And then finally, the concrete would be poured over the top. And what you ended up having was a floor with a series of beams or joists that supported the floor. And each of those was separated by a hollow terracotta block. And that gave you not only a much more lightweight floor, but it gave you a ceiling for the floor below that was flat and could be plastered over. And that had the effect of being able to reflect light much more adequately into the inner depths of the room. And that was important at the time because the lighting was, for the most part, natural light coming from the outside. It was not the ability to illuminate the interior of these factories with the existing lighting methods of the time was actually very poor. This is a picture of a ceiling of one of the buildings at the Packard plant. The plaster obviously has fallen off, but you can see how the concrete beams are embedded and the beams are separated by the hollow terracotta tile. So in 1903, Julius founded his own company. He left Albert's partnership and started the Truss Concrete Steel Company, or Trusscon as it was often called, to manufacture and sell his steel reinforcing bars. And one of the partners in Julius's new enterprise was his brother Albert. So Albert was a very involved partner in Trusscon. So what you have when you put all this together is something that looks like this. You have a framework that's steel reinforced concrete. The columns are steel reinforced concrete. The ceiling is flat and typically light reflective. And if you're not filling the open space between the concrete structure of the building, you can put windows in, or you can fill it with more hollow terracotta blocks. To the extent that you often see bricks on the outside of these types of buildings, the bricks are there purely for appearance's sake, to cover up the concrete frame, depending on the type of building that it is. The first building in Detroit to be constructed using this new method was the Burroughs factory at the corner of 2nd Avenue in Amsterdam. It's gone now, but it was the very first building to use Julius's new method. And if you look right here, you'll see an interesting sign. And if you look closely at it, it says floors, roofs, and lintels, Kahn system of reinforced concrete and hollow tile. And it was the Truss Concrete Steel Company that not only engineered the concrete work, but Julius's company also constructed the building. So at that point, he had an engineering firm that manufactured the reinforcement bars and a construction company that built the buildings, because there were very few companies at that time that had any experience with concrete construction. Now, the 1904 building had the roof and the floors were of reinforced concrete, but it still used iron columns to support those floors. A year later, the first fully reinforced concrete building in Detroit went up, and it was an addition to the Burroughs plant. You can see the original building on the right there, and the new building on the left under the arrow. 1905 was a huge year for Julius's company. Trusscon was selling reinforcement bars and tile throughout the country, literally hundreds and hundreds of buildings, including this one, the Blenheim Hotel in Atlantic City, which was the largest concrete building in the world at that time. The following year, 1906, Julius's company had established well-functioning offices, sales offices throughout the country, particularly in the industrial heartland. And both the Buffalo and Cleveland offices secured some very significant projects that year. As soon as Trust-Con found out that a plant was being contemplated, they'd send their salespeople in to convince the owner that they should go with reinforced concrete rather than either steel frame, which was more expensive, or the inexpensive but fire-prone mill construction buildings. So of these 3 contracts they secured in Ohio and New York for automotive manufacturers, the first one was the Garford Company in Elyria, Ohio. You see that building under construction, and you now see it as well as the building looks today. Second was E.R. Thomas, that was in Buffalo, New York. You see the building under construction there and how it looks today. Now, the interesting thing about these 3 buildings is that when Trust-Con went in and sold the owner on using the reinforced concrete method, they also recommended that they hire Albert Kahn as the architect, which made sense to them because Albert had experience designing automobile factories. He designed the Packard factory. He also had experience building with reinforced concrete, having worked on these buildings for the Burroughs Corporation. So in 2 of these 3 cases, Albert was hired as the architect, but in the 3rd case, the company Pierce Arrow was very stubborn and insisted on sticking with the traditional construction that was recommended by their architectural firm Lockwood Green, until their existing factory burned to the ground, at which point they immediately got on the phone with Julius's company, told them that they wanted to build with reinforced concrete, and also they wanted to hire Albert to work directly with Lockwood Green as the consulting architect, and Albert would be responsible for approving every plan used for the new Pierce Arrow plant. You see a photograph at the bottom of the screen here of Albert's signature on one of the architectural plans that he had approved the way it had been designed. Then back in Detroit, Albert had an order from Packard to add 2 very large buildings to their complex, buildings number 11 and 12. Now here's where it gets interesting. The 3 jobs that Trust-Con sold, Garford, Thomas, and Pierce Arrow, if you add up the total amount of square feet of those factories, come up with 485,000. You add to that the Packard buildings, you come up with a total of 575,000 square feet of new factory space, all designed by Albert Kahn, all built by Trust-Con. It was the majority of all new US auto factory space built that year. And as you might imagine, that incredibly impacted Albert's reputation as an industrial architect. And between 1905 and 1907, his business was transformed dramatically. In 1905, Albert's firm had 23 jobs. Only 4 of those were factories. They were very small factories. By 1907, Albert's firm had doubled the number of jobs in just 2 years, and the number of factories had grown to 19, making up more than 1/3 of his entire company's work, probably far more than 1/3 in terms of the dollar volume of that business. The next year, Albert was in great demand as an industrial architect. He constructed buildings throughout the country, many obviously in Detroit, but also in other cities, including the massive Mergenthaler Linotype factory in New York City, which remains in use to this day, though Mergenthaler has gone from the scene. And many of these other factories are still operational. A few years later, Albert had, as the leading designer of automobile factories, obviously come to the attention of Henry Ford, and Henry hired him to construct his new manufacturing facility in Highland Park. And while that plant was being designed, Albert's chief designer, Ernest Wilby, had the brilliant idea of filling the entire space between the concrete frame members of the building with glass. And the reason this was a good idea is, for one, it lowered the cost of installing the windows, but more importantly, it allowed the absolute maximum amount of light to enter the building, which is important, as I said, because the incandescent lighting of the time was just not up to the task of properly illuminating the interior of these plants. These windows also had operable sections within them that allowed for very efficient ventilation of the building. And you can see, looking at, this is a Packard plant on the left side, the old windows were just standard double hung windows like you'd have in a house. And they compared very unfavorably with the steel sash that held in place these multitude of clear glass windows on the new factories. And interestingly enough, the major manufacturer of these new types of windows was Julius's company. Because Julius's company, keep in mind, was a steel forming company, not a concrete company. The concrete company that Julius had constructed buildings, but they didn't make concrete. So the final version of this type of industrial structure you can see in the Burroughs factory that was built in 3 sections between 1910 and 1919. You see here what it looked when it was completed back then as Burroughs. And today these buildings are still in use. Some of you may be familiar with them, those Detroiters who have driven down the Lodge and seen the Henry Ford Health Systems complex just east of the Lodge and just west of 2nd Avenue. Now, Henry Ford got it in his mind that the idea of building these multi-floor factories was not the most efficient way to go about it. Finally decided that Albert Kahn had been right back in 1903 with these multiple buildings distributed over an area. And he decided to build an entire new factory at River Rouge. And here you see one of the most iconic buildings from that plant, the Ford Glass plant building, which is hard to tell from these photographs, but the entire building is encased in clear glass panels, many of which open up. You can see on the roof and on the side of the building that they open up to provide adequate ventilation to the building. And really, at this point, what the factory had become was a concrete floor with a very lightweight skin of glass surrounding it just to keep the elements out. A few years later, 1938, you see here the Dodge half-ton truck plant, a very modern looking building. Again, it's almost entirely enclosed in glass with operable windows to provide adequate ventilation. Now here you see, and Leslie, this is for you. You insisted that I include an explanation of this. Here is the Packard Foundry building from 1910, and it's a good example of how Albert engineered these buildings to function with natural illumination and natural ventilation. You can see on the left here how natural light entered the building and was able to illuminate well every square foot of the work area. And on the right, you see how cool air was brought in from the sides of the building and then vented out through the top of the building, just through natural gravitational or heat circulation. One other thing I'll point out here, you see in the middle of the building there's a crane. Most of you are probably familiar with it. Some of you probably not. But in the era before forklifts, this craneway was the manner in which materials, parts, assemblies were moved around within the factory. The craneway could move back and forth across the plant and could haul materials left and right. And Albert's clever design here, which he later patented, was to construct the building in such a way that the craneway was supported almost in midair by the walls of the building, which were further out. So that left an area unencumbered by columns underneath the ends of the crane. Now, if you look at Julius's company, just by 1908, his materials, his reinforcement bars have been used to build over 5,000 buildings just in the US and Canada alone. He had also by then developed distribution networks throughout the world. His system, the Kahn system of reinforced concrete, was the dominant method of building reinforced concrete buildings everywhere in the world at that point. And Julius's company was extremely successful and quite large. I think at one point they did about $50 million worth of business, and that was back in the 30s when $50 million was real money. By the middle of the Depression, Julius was nearing retirement age, and in conference with his chief managers, they decided to merge the company with Republic Steel, and Julius became Republic's vice president of product development. Around the same time, 1938, Architectural Forum magazine printed a review of Albert's business. And one of the things that they maintained, they had determined through research, is that nearly 20% of all the architect-designed industrial buildings in the US were designed by Albert Kahn's firm, an incredibly impressive statistic. And Albert's firm continues to operate today, Albert Kahn Associates Incorporated. They occupy 2 floors in the Fisher Building. Well, given all of these developments, Julius and Albert were quite pleased with themselves and the work they had done. And got a few minutes here. I'll just touch on a couple things that I think are tangential but important. The very first concrete automobile factory constructed in the world was actually the Cadillac Motor Car Company plant in Detroit. And you can see here, I've clipped a page from George D. Mason's diary. George Mason was the architect that designed the Cadillac Motor Car Company plant. And you can see here that he makes a note on September the 6th that he agreed with Julius Kahn over the phone that Julius would construct the plant for him of reinforced concrete. And the very next day, Julius ran an ad calling for laborers and teams to arrive at the Cadillac plant to begin construction. About 6 weeks later, this is how the building looked. You can see the formwork for the first and the second floors. You can't see the basement. It's also a reinforced concrete floor, and they're working on finishing the third and final floor of the building right here. And if you look closely, you can see Julius's reinforcement bars actually being used here on the plant, laying on the floor to be used to reinforce the floor, and the vertical ones for the concrete columns. This is how the building looked when it was completed, November 19th, 1905. And on the right, you see how the building looks today, not significantly different and still in use for a display company, Westcott Paper. And just to orient you, here's where the Cadillac or former Cadillac plant is located, just south of the train tracks in Midtown. And if you go down there, 450 Amsterdam, you can actually see in person one of Julius's reinforcement bars right here on the first floor of the building, where it's concrete's been chipped away, I guess, by trucks that were not too carefully driven. The building number 10, which many people have heard about and is often claimed to be the first concrete automobile factory, was actually constructed immediately after the Cadillac plant. You can see here the various advertisements and the notifications of the building permits being issued. And not only that, here's an interesting point. The cost of the Cadillac plant, $75,000, compared to the cost of building number 10 at the Packard plant, $15,000. building number 10 was really just a proof of concept to convince Packard that they were wise to go ahead and use reinforced concrete. But the Cadillac Motor Car Company, they were all in with building with the reinforced concrete method, perhaps because their building was right across the street from the Burroughs factory and they had seen it constructed. And here's another interesting little bonus slide. People often ask me what the difference is between these mushroom top or martini glass columns. And it's simply a different form of concrete reinforcement that was developed around 1910 and used fairly extensively after that. It was called mushroom top, not because of the way the column looked from inside the building, but because if you look in the lower left corner there, the reinforcement took on a mushroom cap shape before the concrete was poured. So hopefully that gives you a little bit of insight into that. And I will end with, like Michael Hodges did, my shameless promotion for my book, which talks about Roland's work in Detroit, but also a great deal about Albert Kahn, for whom worked for more than a decade and was a key member of that organization. And I would be happy to answer some of your questions.
Okay, Michael, thank you very much. And from the volume of questions, I think people have been really fascinated by all this. So one comes up from Levi. Julius had his company apparently headquartered in Youngstown, Ohio. Is that true? And why there and why not Detroit?
It's partly true. Julius started his company in Detroit in the same building as Albert Kahn's offices were in. And he later built a building, the Trust Concrete building in Detroit. It was Detroit's first steel reinforced concrete skyscraper. And then in later years, Julius moved the headquarters of the company to Youngstown simply because it would be easier to have his plant located or his offices located where his plant was located. His plant was located in Youngstown simply because it was located right next to the steel plants in Youngstown. So it was just a matter of following his production facilities to Youngstown, Ohio.
Okay. And in fact, we have a shout out from the Steel Museum in Youngstown, and they have some attendees with questions here. And one of which is, do you know of any exhibit of Kahn bars suitable for museum display?
Well, I would wish that there were, and that somebody would find one. I went with a number of our members of the Albert Kahn Legacy Foundation to the Packard plant in search of the very thing that they've asked about, and we came up empty-handed, unfortunately. So we are all looking for that crucial bit of display exhibit material for our exhibit, which will occur April to June or April to July, actually, of next year at the Detroit History Museum. And we would love to find a piece of Julius's reinforcement bar. And if we get desperate, I might see if we can get permission to remove that piece from the former Cadillac Motor Car Company plant on Amsterdam.
Okay, very good. Dave asks, did Albert Kahn's non-industrial buildings, such as Hill Auditorium, also make use of the Kahn concrete system?
Absolutely. Just about every building that Albert designed between 1903 and sometime in the 20s used Julius's method. They weren't all necessarily constructed by his company. They got out of the construction business around 1908. But Julius had 76 patents over the course of his lifetime. And many of the inventions that he came up with were in use far after the time that his reinforcement bars were superseded by newer technology. So even if his reinforcement bars weren't used in later years, his other inventions were. In fact, a few years ago, I happened to make a trip to my old high school, and they had the ceiling, the drop ceiling panels taken out of one room. And I looked up, and what did I see but the high rib construction material that Kahn was selling in 1927 for constructing reinforced concrete buildings. Who knew? But there it was in my high school. I'm sure it was probably in your high school as well, if it's an older building.
Sure. One question from Anonymous asking about Wilby's pioneering development of the steel sash window. What's the source material for that? Is there stuff you can point people to who want to learn more about that?
Yeah, Ernest Wilby's application to the American Institute of Architects describes that, and it's also referenced in a number of secondary sources that are easily found online. It shouldn't be difficult to locate that. And I believe that Wilby's application is available for download at the American Institute of Architects website.
Okay, very good. Leslie is asking that a lot of these factory buildings had multiple basements. What was that all about? Was that for part of the infrastructure to hold them up, or she asked if that was a way to hide booze during Prohibition?
Most of these buildings predated Prohibition that we're talking about. But the reason for the multiple basements is that's how they had to house the mechanical equipment, the heating, ventilating, electrical equipment. Oftentimes that equipment was taller than the typical height of a basement. So you'd have a portion of the basement that had that was excavated lower and had a lower floor. That was really the main reason for that. And oftentimes when you go into those buildings, you're not aware of that because that heating equipment has been replaced by newer equipment, and so it isn't obvious what equipment was there at one time that required a greater ceiling height.
Okay. Anonymous also asks, how many people were employed by Albert Kahn's firm, architects versus engineers, and then any idea whether the architectural staff liked to work on the factories, or was it more from money making, a boring kind of work for them?
Well, I don't think I can answer the second part of that question because I wasn't there, and I don't want to talk about something that I really don't know about. But there are probably people that work on that type of work today that could answer it. As for the former question, it really depended on what time period you were talking about. I've seen 200 people, 300 people, 600 people. During the war, there were probably more people. During the Depression, fewer people. There was an office in Moscow for 3 years, and there were building, or I'm not sure if it was Moscow, but in Russia, when they were designing the factories for the Soviets, they had, I think, 25 people in the office there. They had offices in other countries. That's probably a question that requires its own thesis in order to come to an accurate answer.
Okay. Claire Zimmerman says that there is a sample of a Kahn bar in London, and she would be happy to supply a photograph of one. So how can she send that to you, Michael? Claire,
I really appreciate that. You've got my email address, or I'll send you an email, and we'll get together on that. And perhaps it could even be spirited out of London for a temporary exhibit. But I really appreciate you letting us know about that. Thank you.
Good. Peter gives your book a shout out, says it is excellent, all capital letters.
Well, thanks, Peter. I knew you'd come through for me.
Okay. Very good. The term pre-stressed concrete, what is that compared to what Julius was doing?
All right, well, that can be very complicated, but I will give try to give a summary answer. We looked at how these reinforcement bars that Julius manufactured were placed in a beam, and then the beam would be loaded up with weight until it ultimately gave out and the reinforcement bar snapped. Now, on the way to the reinforcement bar snapping, the steel would be stretched and stretched further, and the beam would sag somewhat. When you pre-stress a reinforcement bar in a beam, what you're doing is you're inducing that stressed condition already, so that as weight comes up on the bar on the beam, the bar is already holding it so that there's less deflection in the beam. Think of the reinforcement bar as like a rubber band. Rubber band stretches quite a bit before it actually begins to do any work. So you're doing essentially the same thing with the steel reinforcement bar. You're taking that stretch out of it, and the reasons for that are more complicated than I understand, and so I won't go into that. But that's essentially what's happening.
Okay. And Lowell is asking, hi Lowell, he's asking about your opinion on Kahn's influence on Bauhaus design and modernism. And this is something we've talked about
Yeah.
with Mike Hodges, and I'll talk about with the next lecture, but you go ahead.
Yeah, again, this is one of those things that I'm not all that qualified to talk about. I believe that Kahn was influential either voluntarily or involuntarily because his buildings were very utilitarian in appearance. And that was one of the accomplishments of Albert, was that he was willing to forego his inclination to be an architect when it came to designing industrial buildings. So he was willing to let go of the idea of making the building look ornate or decorated, and simply focus on making the building the most effective it could be at doing the job that it was intended to be built in order to accomplish. There's a whole line of investigation that could go into Albert's influence on the Bauhaus, but that's not something that I can really delve into myself.
Okay. Levi asks, was Julius ever honored by University of Michigan, his alma mater?
Not that I'm aware of.
Yeah, it's funny, Michael Hodges went last time about how Albert's reputation was kind of superseded as modernism came along, and his work was, and Julius is perhaps almost even more forgotten, despite his
Right.
enormous influence on architecture and engineering.
Yeah, he was in many ways a very modest person and a very self-directed person. His chief interest was in devising clever ways to advance the technology of manufacturing and manufacturing building construction. He was not all that interested in fame or fortune, like the architects and engineers that we hear about all the time. There's more flash in the pan there than there is achievement, I think, in many cases.
Mm-hmm. A shout out from Lori in LA, and she asked if there's any Kahn buildings in California.
Yes, there are. As a matter of fact, there's one in Richmond, California. There's a plant there that was recently added to the National Register of Historic Properties. And I think it's a museum now that houses the one of the World War II Rosie the Riveter type things. I can't remember the details. I'm sure that if you Google that, you'll find it. But that's just one of many buildings. Almost all of the Ford buildings, factories constructed in the teens and 20s were designed by Albert, and it's not hard to find information on those structures.
Well, Michael, I want to give you one more chance to promote your book. It's published by Wayne State Press, correct?
Correct?
And it's available where? Where can people buy your book?
Well, it was available for 3 years on Amazon, and now Amazon says out of stock. We'll let you know when it's available.
Ah,
Uh, I think if they got a couple or 3 orders that they would immediately get it back in. But failing that, you can certainly order it from Wayne State University Press. Most local bookstores downtown have it. Pure Detroit usually has it when they haven't sold out. And if all those fail, you can get in touch with the Albert Kahn Legacy Foundation, and they'll get in touch with me, and I'll send one out to you with my autograph in it.
very good. Okay. And your contact then? Do you want to? Do you have a some sort of at where people can reach you?
Well, my email address is mgsmith.usa@gmail.com.
Okay.
Or you can reach me through the foundation.
And Bill in Chevy Chase, Maryland says, thanks, Michael, from your architect fan from Chevy Chase, Maryland, who grew up in Youngstown and knew many people who worked for Truscon. Kahn's buildings, by
Thank
the
you
way,
so much.
Kahn's buildings were featured in architectural history books of the 1950s. So they definitely influenced at least late modern architecture. So as you said, that'll be something we can talk about for a long time. Oh, and the Youngstown people, Youngstown State University has now ordered your book, even as we speak. Okay.
That's great. Thank you, Bill, for that one.
Right, right.
Bill has been a tremendous help to me.
Yeah. Okay, good. Well, I think on that note, we've done most of the questions. So I'm going to thank all of our attendees tonight and remind people that the Albert Kahn Legacy Foundation website is albertkahnlegacy.org. So go there for more information about upcoming events, our bike tour, and future lectures and other events. And Michael Smith, we really want to thank you so much for sharing your knowledge and your history of this really important field. Just as a Detroiter who knows a lot about architecture and a lot about Detroit history, I learned an awful lot tonight. So I really want to thank you personally, and I'm sure everyone else does too.
Well, I appreciate the Albert Kahn Legacy Foundation giving me the opportunity to spread knowledge, and I hope everybody's enjoyed it. There'll be more of these. Legacy Foundation is, I think, doing some of the most interesting work in architectural history in the Detroit area, and we look forward to other people joining us in our efforts. Thank you.
Great. Okay. Thank you, Michael. And that's it, everybody. We'll see you next time. Okay. Thanks very much. Bye-bye.
Bye-bye.